All right, this is take two, hopefully with sound. Yeah, so this presentation is the pragmatic prior, and it's a way of amortizing rational speech acts. And the idea is to reach the few people who might be interested in these kind of stuff. My email is right here on the bottom, and it's my Twitter, so also here. So if this kind of stuff is of interest to you, just kind of reach out to me. That's really kind of the entire goal of this presentation. And I'm going to assume some familiarity with the rational speech acts by Frank and Goodman. Okay, cool, let's get started. So rational speech act is a algorithm that's kind of a chain of recursive Bayesian reasoning, building a kind of speaker and listeners on top of each other, right? And then if you want to look at it from a computational point of view, then you have these matrices. You start with the meaning matrix M. Here we have kind of Boolean matrix of ones and zeros, and then you normalize the rows and columns and rows and column, and you keep going, and then you build this chain. And so you can build this chain of arbitrary length, right? As long as the chain the one node of the chain depends on the previous one, you just normalize it in one direction, and you have this chain can kind of go on forever. And so we can ask a question for any listener in the chain, which is some kind of a two-dimensional matrix, right? Like, what structure does one of these matrices have? And so the key result of this work is that for any listener in the RSA chain, it could be exactly represented as the meaning matrix as you are given, multiplied pointwise with another matrix, which is the outer product of two vectors, the row vector and the column vector. And so the meaning matrix is given to you from the RSA before the RSA, right? You start with it. And the row and column vector are basically the work of the RSA, right? And so the result basically says all the work of the RSA can be kind of distilled entirely into these two vectors. And so the proof just is quite straightforward. And you start with the meaning matrix M, and then you follow a sequence of alternative normalizations of rows and columns. And you can simply kind of collect all the row normalization together into the one row vectors, and then you can collect all the column normalization into the one column vector. And these operations they kind of commutes, right? And so you can collect them and pretend that you kind of aggregated all of them together, and that's how you end up with these two vectors. And so what are some consequences of this result is that in the RSA computation, instead of kind of maintaining the entire matrix of any of the listener or speakers, you can just maintain two vectors instead of like all kind of n squared number. You can maintain just like two n numbers in the RSA computation. And the second consequence is that if you're willing to kind of don't think about the listener as a proper distribution and just kind of proportional, which is very useful for ranking, right? You just want to say, well, the probability of this hypothesis is higher than the other one. You can only use, you could get away with only one vector, which is the title of the presentation, which is the pragmatic prior. And so to kind of perfectly capture a listener anywhere on the RSA chain, you only need a prior over just the hypothesis, and multiply that by the meaning matrix. It's possible to represent any listener in this manner. And the third consequence is that since the RSA can be kind of represented in this fairly simplistic, like basically two vectors of numbers, right? Then there might be some alternative, or it points to maybe potential alternative derivation of the RSA algorithm without the actual kind of normalization. Maybe you could write it as an optimization procedure and directly optimize for these two vectors of number directly. That's it. So yeah, if these kind of results are roughly interesting, these are my contacts. So please, reach out to me, and we can hang out and talk about RSA and the math around it. Okay, that's it. Thank you. Goodbye.